If you have two vectors a and b, that are at right angles to each other, they are called orthogonal. Mathematically, if the vectors are orthogonal, their scalar product or dot product, a dot b, equals 0. Two functions can also be orthogonal. Take two functions psi I and psi j. The scalar product for these two functions is defined by the integral from negative infinity to plus infinity of psi I star of x times psi j of x dx. The integral runs over all space, assumed one-dimensional here. In three-dimension, of course, this would be a triple integral. We can abbreviate the integral using bracket notation. It's equal to open angle bracket psi I vertical bar psi j close angle bracket. As always in bracket notation, the complex conjugate of the first function in an integral is implicit in the definition of the bracket symbol. Two functions for which this integral is 0 are called orthogonal. Let's look at an example. Take the two functions x and x squared. The integral to check for orthogonality is integral over all range of x times x squared dx, which equals the integral over all space of x cubed dx, which evaluates to 1/4 of x to the fourth evaluated from negative infinity to positive infinity, which turns out to be 0. Therefore, the two functions are orthogonal. They satisfy this relationship. There is a way to obtain this result without having to evaluate the integral, using symmetry arguments. Let's plot the functions. The function x squared is an even function, which means it is symmetric about the vertical axis. Or mathematically, f of x equals f of negative x. On the other hand, the function x is odd. It satisfies f of x equals negative f of negative x. The product of an even and an odd function is odd, and the integral of an odd function is always 0, since the left and the right halves of the integral cancel. So x cubed is odd, therefore the integral of x cubed over all space equals 0. Here's another example for this type of symmetry reasoning. Take the two functions psi 1 equals e to the negative alpha x squared and psi 2 equals to x times e to the negative alpha x squared. If you plot the two functions, we get for psi 1 a simple Gaussian function, and for psi 2 this type of curve. Psi 1 is obviously even, and psi 2 is clearly odd. Therefore, the product of the two is odd, and the integral is 0. If the product of the two functions were even, we would have to evaluate the integral. Here we were lucky, and the integral was 0 by symmetry. Orthogonal functions are very important in quantum mechanics. The eigenfunctions of any operator used in quantum mechanics are orthogonal to each other. So, if you have a set of eigenfunctions for, say, the Hamiltonian operator, which satisfy the eigenvalue equation of the Hamiltonian operator, h operating on psi I equals ei times psi I, these eigenfunctions psi I satisfy the scalar product of psi I psi j equals 0 as long as I is not equal to j. If, in addition, the functions are normalized, we have scalar product of psi I psi j equals 1 for I equals j. A set of functions that fulfills these two properties is called an orthonormal set. In summary, the key point is that the eigenfunctions of a quantum mechanical operator form an orthonormal set. This applies not only to the Hamiltonian operator, but to any other quantum mechanical operator we are dealing with, like the momentum operator, the position operator, the kinetic energy operator, and so on. This is a very important property and worth remembering.